Science. So we've gotten through the first section of our chapter on Earth's interior, and now we're going to the second section. So in the second section, what we're going to do is we're going to just focus more on each individual layer and some of their properties, which I'm going to want you to know. And I'll keep it pretty basic. And after this, you're going to get a homework that reviews everything, okay, which you're going to have to fill out. So you can fill out that homework based upon these notes, and I'll try to annotate where I can. Okay, so first of all, the crust. This is where you and I live. All right, so this is where you and I live. No human's ever been below the crust. Nothing alive is below the crust as far as we're concerned. And there's two types of crust. There's continental crust and there's oceanic. So continental crust is made of our good old friend granite. All right, not granny, but granite. And its consistency, of course, is just solid. Density is very low. Okay, it's going to be low density, and it's going to be very thick. It's usually going to be between 0 and 60 kilometers thick. All right. Oceanic crust, on the other hand, that's what's going to be at the bottom of the ocean. So if you swam to the bottom of the ocean, that begins the oceanic crust. This is made of our good old friend basalt. Okay, and consistency solid, of course. Density is high. It's going to have a very high density. You may remember that from your lab that we did together. And the thickness of this is going to be thin, usually between 0 and 5 kilometers, so about 3 miles thick. So real thick for continental, real thin for oceanic crust. Okay, the Moho, or the Mohorovich discontinuity, we call it the Moho. The Moho is just the boundary where the crust ends and the mantle begins. If you're going down. If you're coming up, it's where the mantle ends and the crust begins. So where crust transitions into mantle, a zone that becomes gooey consistency, and that is called the Moho. Okay, it was discovered by a guy by the name of Mohorovich, and for short, people call it the Moho. The lithosphere. Okay, this is all of the crust and the very upper mantle that moves as one big slab that we call a tectonic plate. So what a tectonic plate is when the entire crust and the very upper mantle moves as one great big slab. It's very brittle. If it flexes, it breaks. Okay, and this is why we're going to get into earthquakes and stuff like that. But the thickness of it is typically right around 100 kilometers. So it's solid and non-flexible. Same thing with the lithosphere here. Okay, more properties. It is solid and non-flexible. It is brittle. Like the shell of an egg. If you break it, okay, it's going to crack. So if it moves, it will crack. And that's why you have all these cracks in the surface of the Earth. The thickness is from the surface, where you are right now, to a depth of somewhere around 100 kilometers, about 60 miles. It depends where you are. It could get a little thinner, it could get a little thicker. The Asthenosphere, it's another zone. Okay, so the lithosphere is a zone. Right? It's not like an actual by itself layer, and so is the asthenosphere. It's a zone. So you'll see on your homework it says zone. All right, from below the lithosphere to about the middle of the mantle. So this goes below the lithosphere. So basically, the asthenosphere, as we say, is the upper to middle mantle. Okay, unlike the lithosphere, this layer is very plastic, and it won't crack. Okay, it allows the lithosphere to slide over it. So it's just a zone. And we're going to call it a zone. It's just below the lithosphere. Typically, it's about, from the, like I said, from the top of the mantle down to about maybe the top third of the mantle, something like that. The mantle, all right, it's the thickest layer. It's super, super thick. It's the thickest layer. It is solid, but gooey, as far as we're concerned. It's solid and gooey. That says soldy and gooey. Sorry, I'm doing my best here. Okay, it is solid and gooey. It's made of things like magnesium. It's got some iron in there. Okay, the thickness is very thick. It's 2,800 kilometers thick. So we're talking somewhere in the neighborhood of, off the top of my head, I'm trying to do this, almost 2,000 miles. Okay, 1,800 miles. It is really, really thick. All right, and I'm going to try to upload a video for you guys to watch as well. But it's a thick layer. It's Earth's thickest layer. Okay, The Gutenberg discontinuity. This is another boundary, and this is where the mantle becomes the outer core. All right, just like the Moho is where the crust becomes the mantle, the Gutenberg is where the mantle becomes the outer core. And you guessed it, it was discovered by this dude named Gutenberg. It's also where solids turn to liquid. That's how he found it. He found where the P and S waves were slowing down and the S waves were disappearing. And that's what he called the Gutenberg. So now we get into the most important layer of Earth, and that's the outer core. It is made of lots of iron, and that's the element Fe, ferrous, okay, and nickel. That's nickel, all right. Consistency, guys, it is molten, all right. It is liquid, okay. Its thickness is right around 1,200 kilometers. So we're talking somewhere in the neighborhood of about 800 miles, somewhere in that neighborhood, okay. And why is the outer core very important? Without the outer core, okay, you've got moving iron and nickel. Whenever iron and nickel move, it creates a magnetic field. And this magnetic field is actually protecting you from the sun because the sun is releasing loads and loads and loads of radiation. And if we didn't have that magnetic field, not only would radiation burn up the Earth, okay, also we wouldn't have, our GPS systems wouldn't work. We wouldn't have a magnetic north and a magnetic south. Compasses wouldn't work, okay? So what produces is Earth magnetic field, which creates a magnetic north and south pole. So you can think the outer core for helping you to find places, okay? Your GPS, like I said, it wouldn't work because your GPS relies on finding north and south and all kinds of stuff like that. It's pretty slick, actually. All right, the other thing is that it's going to protect us from the sun. Now, about every 50,000 years, the magnetic north and south poles reverse. It's called a reversal. The record of reversals is kept by magnetite mineral on the sea floor. Magnetite's iron atoms align and point to magnetic north when the mineral cools from lava that has erupted from the seafloor. Striping patterns on ocean floors reveals evidence of seafloor spreading and magnetic reversals. Basically, all I'm trying to say here is that once in a while, magnetic north and south actually flip. So when they flip, if you had a compass and the compass was pointing north, you'd actually be walking south. And this happens about every 50,000 years. We haven't had one for 100,000 years. So if you're asking yourself right now, wait a second, they happen every 50,000 and it's been 100,000. Are we due? Yup. And weird things begin to happen on the Earth when it flips. And we could be going through a reversal right now, actually. Okay? Well, things are pretty strange, aren't they? This is just the seafloor, and this is actually the Atlantic seafloor, and this was discovered by a scientist by the name of Harry Hess after World War II. And what he found was as he progressed from the east coast of the U.S. Across the Atlantic Ocean, okay, he could tell that there was at the bottom of the seafloor, there was a mineral named magnetite, came from eruptions of volcanoes. And as he crossed on a boat, he would see that these minerals actually recorded that, what magnetic north was or south was at the time. So this was a normal time, and then a few miles later was a reversal, and then normal, and then reversal, and normal, and reversal, and normal, and reversal. And as you go from Europe and you go towards the United States, the exact same thing happens in the exact same pattern, indicating that these rocks right here and right here are of the same age. And these rocks here and here are of the same age. And these rocks here and here are of the same age. And it helps us understand that the seafloor was spreading. So we'll get into that later with plate tectonics, okay? It's very hard to describe to you, not being in class with you guys right now. Now, another thing about the outer core is it protects us from radiation from the sun. Okay, this is all the outer core. Without a liquid outer core, we would not survive, as the radiation from the sun would exterminate the Earth. So the magnetic field that's surrounding the Earth, created by the outer core, actually prevents us from radiation from the sun. The basic type of radiation it protects us from is called X-ray radiation. So if the outer core stopped moving, life on Earth would not be possible. There's a great, terrible movie. Okay, I'm going to say a great, terrible movie that came out called The Core. And the premise of the movie is all about the fact that in the movie, Earth's outer core stops moving, and they're trying to restart it. It's a great concept. Love the concept. Terrible movie. Okay, But I did show it in class before. I have shown it in class before, and if we come back, maybe we can do that. All right. Finally, the inner core, the last layer. The inner core is also, like the outer core, made of iron and nickel. Okay. The consistency this time is solid, and its thickness is right around the same as the outer core. It's about 1,200 kilometers. It is a solid ball of iron and nickel. Okay. And why is it solid? Okay, so a couple things here. It is the very hottest layer of the Earth, the inner core. It is the same temperature as the surface of the sun. And the surface of the sun is around 10,000 degrees Fahrenheit. That's what makes it an orange star. However, it is solid. And why is it solid? It is solid because it's of the pressure down there. Okay, so this layer is solid due to the enormously high pressure. When you increase pressure, you increase melting temperature. So let me say that again. If you increase pressure, you increase the temperature at which something melts. So because the pressure is so high down there, you would have to get the temperature to be much, much, much higher down there to make it melt. Okay? And that, guys, is the end of the layers of the Earth. The next thing we're going to do is start looking at Earth's plates. Okay? And we're just going to talk about their interactions. And it's going to be a little different than what I've ever done before, but that will be the next lecture. Okay, so thanks for listening, and we'll talk soon.